Good.
So welcome everyone. Welcome to the first workshop on heterogeneous memories. And sorry, I'm getting messages with respect to this organization workshop. Thank you for joining us. We have an excellent agenda. I guess you will all have it, so I can paste it on the chat. I won't show slides to be faster today. And so one of the things that we want to warn everyone is that we will be recording this workshop. So if anyone doesn't want to be recorded, please leave. I think we warned everyone. Actually, it's already recording. So we are recording this workshop to display it on the website later on. So the talks will be 30-minute slots. It will be 25 minutes plus 5 minutes Q&A. And when the panelist is talking for 20 minutes, we will interrupt him and let him know that is him or her that it's 5 minutes to go. We will try to do that without being intrusive, like when he's changing slides or something like that. And Harald, am I forgetting something?
No, nothing.
All right. Do you want to say a few words?
No, I think you did an excellent introduction. So
okay.
Yeah, this is the first incarnation of this workshop. We are very excited on the different topics that our panelists are presenting today, and also for the panel session that we will have after the break, after Adrian Jackson's presentations, that will be led by Marie-Christine Solly. So I hope that everybody will enjoy this event.
Great. I forgot something apart from the panel, of course. Thanks, Harald. We will favor live questions by voice. You can also post your questions on the chat, but we will favor voice ones. So feel free to raise your hand and we will moderate questions and give you a voice to ask live to our presenters. So are we good to go with the first panelist, Harald?
Well, Michal, you ready?
Yeah, I'm ready.
Good.
Okay.
Can everybody hear me? Yeah.
Yes.
Yes.
Okay, great. Let me share my presentation. Could you see my screen?
Yes.
Or not?
Yeah.
Okay.
Yes.
Yeah, great. So I believe we could start it, right?
Go ahead.
Yeah, okay. So this is a 25 minutes presentation where I'm going through a lot of information very fast. So if anyone got a question, there will be a 5-minute slot time after this presentation where I will hopefully answer for some of this question. A couple of words about me. My name is Michal Biesek. I am software engineer who is working in Intel Data Center Group division. My daily work activities are related to enabling different applications, mostly databases, to work with persistent memory. I'm also a lead developer in Libmemkind project. Memkind is an interface which allows and enforces different memory types and different memory policies used in inside one heap management. This will be main topic of my talk, as well as Intel's approach to heterogeneous memory architectures. So today's multi-core processors are used extensively in high-performance computing, but new memory hardware technologies bring some fresh approach to extending this performance even more. Memories like packageable addressable memory or non-volatile high capacity DIMMs offers different possibilities compared to standard DDR memory. So challenge with managing complex memory architectures even with single memory system is not a trivial task, but with a new hardware things gets even more complicated. So one of the solutions is that we could use multiple disjoint libraries to handle allocation for each memory individually, but this will be a hard road for developers. What Intel proposed is a unified solution which could be used to simplify effort for enabling new memory hardware. So let's get back to 2016. In 2016, the Intel next generation Xeon 5 processor product, code's name Knights Landing, brings to the table new memory technology. Knights Landing offers access to two types of memory. Besides standard DDR4 modules, it provides also a high bandwidth on package memory called multi-channel DRAM, in shortcut MCDRAM. Compared to DRAM, MCDRAM offers higher bandwidth, about 4 times more than DDR4. It comes with lower capacity than DRAM, up to 16 gigabytes, and is fused on Knights Landing silicon chip. MCDRAM is, of course, name of technology, and a high bandwidth memory is the role which this memory plays. But in this presentation, when I mean high bandwidth memory, I mean MCDRAM. So Knights Landing offers 3 different modes which could be chosen during 3 different operating modes which could be chosen during boot time. Each mode corresponds to match the different programming styles that are already popular. First is a cache mode. In cache mode, MCDRAM can be configured as memory side cache and works behind the operating system, and behind the scenes is seen as last level cache between the L2 cache and on the platform DDR4 memory. All requests first goes to the MCDRAM and for a cache lookup, and then in case of miss, a request is sent to DDR. Advantage of the solution is that it has no action required for the developer to use this high bandwidth memory in an application. Downside of the solution is that cache misses could be pretty expensive. So the second one, most interested from Libmemkind perspective, is flat mode. In this mode, MCDRAM is treated as standard memory in the same address space as DDR, but is presented to us as separate memory only NUMA node. It is, let's say, a virtual NUMA node because the both memories works on the same inside of same socket. Software modification and execution environment are required in this mode, but if the developer won't know what it's doing, it could achieve better performance than in cache mode. And the third one is the hybrid mode. It's kind of mixed one from the previous 2 modes, but brings benefits from 2 previous models, but results with smaller site for each mode. As you can see, MCDRAM can be used as a cache or as distinct NUMA node, allocatable memory, or somewhere in between. With the different memory modes, it becomes very challenging from software perspective to understand the best mode suitable for an application. The easiest way is to allow OS do the job and use cache mode. Second possibility is fit the whole application to MCDRAM using NUMActl command. Another one's bound all allocations to high bandwidth memory. But the third case is the most interested one. If user could point the application data structures that are, let's say, most bandwidth sensitive, then we could manage different types of memory inside one application. And Memkind address this long-standing software gap for managing multiple kinds of memory. Not only DRAM or MCDRAM, which will be presented later, is considered persistent memory. So with motivation to Libmemkind, we got 2 approaches. First, a simple one, where we could use 2 different allocators. And the second one, the more general solution with memory management systems for different types of memory. So Libmemkind, as I already mentioned, is a heap manager. It's basically a library where you have absolute control where you place data on user level software. This is done by provide an abstraction for different memories. Abstraction take a form of different pools, different memory heaps with different performance characteristic, which is called internally by a memory kind. Memkind library is written in C. It is trade safety, open source, and available on Linux. It is built on jmalloc allocator. What it means that the memory allocation algorithm are completely handled by jmalloc. We use jmalloc feature called extent management hook to provide in Memkind additional layer responsible to allocate memories from specific NUMA nodes. And as you can see, Memkind API is presented as malloc style API, well known for software engineers from example Gelibce implementation. So Memkind delivers two interfaces defined in the header files hbw-malloc.h and memkind.h. First one is, let's say, convenience for users who only want to use high bandwidth memories. It basically minimizes the code changes. You could just add HBW prefix for calling memory allocation functions like malloc, calloc, or free. Internally, this interface calls memkind.h interface functions. So the second interface, memkind.h, it provides a heap management API with additional first argument, memkind, the memory kind. Main advantage of the solution is flexibility. Interface is not limited only for MCD-RAM, but is open for additional memory types, including user-defined one. With memory kind, which will be shown in future slides, user can control to which physical medium put their data. Long story short, memory kind is a separated memory pool with different performance characteristics. These pools are treated as independent memory heaps. Memkind allows to manage those heaps. Static memory kinds described on this slide are predefined objects already available in library. The closest adjective here refers to local and remote memory access in context of NUMA node distance. So NUMA node distance matrix is calculated in base for ATSP table and memory architecture. And the default behavior in Linux on NUMA system is memory will come from the NUMA node with the smallest distance from the CPU of the calling thread. So the closer the core the task is running on, the data is on the data the task needs to operate on, the faster we have access to this data. So in case of MCD-RAM and DRAM placed on the same socket, smallest NUMA distance belongs to DRAM. And we have also preferred variant. And in this variant, Memkind we allocate, we perform allocation to MCD-RAM using MCD-RAM first, and then if allocation will fail, it will use nearest DDR memory. So the DDR memory from the same socket. So let me talk about more about persistent memory. Here is short overview what persistent memory is. Persistent memory, shortcut PMEM, describes technology which is directly byte addressable, while the contents are non-volatile, preserved across power cycles. It is a new type of memory, DDR4 socket compatible, which can coexist with conventional DRAM memory. It has aspects like memory and aspects like a storage, but it doesn't typically replace either memory or storage. Instead, persistent memory is a tier, used in conjunction with memory and storage. PMEM offers greater capacity than DRAM and significantly faster performance than storage. PMEM can be acts like DRAM memory, but we eliminate the need of page cache between memory and storage. Therefore, performance is pretty improved. PMEM is available since second generation of Intel Xeon scalable processors called Cascade Lake. So despite the persistent adjective in the name of physical medium like persistent memory, in case of Memkind, we just want to use the bigger and cheaper volatile memory than DRAM. Persistent memory offers a trade-off between price and performance. And with Memkind, we could manage volatile memory in context of different physical medium. For objects, for example, for objects which required low latency, we could use DRAM, and for non-latency sensitive allocations or large size allocations, we could use PMEM. Persistent memory comes basically with two modes. First is a memory mode. It is pretty similar to cache mode. The faster medium, DRAM in this case, turns into L4 cache. No programming is needed in this mode, and total available memory is presented as sum of persistent memory modules. Updirect mode allows the system to handle DRAM and persistent memory independently. This mode needs code changes and implements the full NVM programming model described on the next slide. So what is important here that today's software operates under the assumption that this data can be only persistent if it's written to slow storage written to the slow storage. But under AppDirect mode, it allows data to be persist at memory speeds. But as I already mentioned, Memkind operates on assumption that we don't want to persistency, we just want to big capacity of this model. So this chart presented on the slide could be pretty overwhelming, but let me summarize it. Block access presented right here rely on buffer-based access. This is basically read and write syscalls for standard file, which is used as in case of storage device access. Despite the persistent memory medium could be treated as storage device, we are interested in software access as a memory, reading and writing to persistent data the same way that it would be read it and write it as to the DRAM. So what interested us most is here is AppDirect mode. For this mode, we don't use read and write syscalls as buffer-based access. We perform load and store operation with memory mapped file access. What is pretty cool here, we could access HMEM without paging mechanism. In other words, without using the page cache, we don't perform necessary copies of the original storage to read and write to Dykes capable storage device. Dykes means directly mapping for persistent memory. In other words, we remove page cache from input-output path. So HMEM device could be configured as FS-Dykes, file system with Dykes capabilities. This allows us to establish direct mappings to persistent memory media. This is represented by this red connection line. And the application program would also communicate with memory through the memory mappings, which were managed by the file system. We return to this with first example how Memkind use HMEM. On the second thought, the blue connection line on the slide represents dev-Dykes mode, which enables similar mapping capabilities as file system Dykes. However, instead of block device that can support Dykes-enabled file system, this mode emits a single character device file. And we return to this with second example of how Memkind use persistent memory. PMDK shortcut here stands for Persistent Memory Development Kit, which is a separate library related to persistent aspects of HMEM. So let me present a short example. For this HMEM scenario, we use a file-baked kind of memory based on file system, which is Dykes-enabled file system. Behind the scenes, the memory kind takes a form of memory mapped temporary file. Since we have file system which could be mounted in different location, we cannot use a static kind solution like those presented in case of high bandwidth memory. We will use a dynamic kind solution, which requires kind management operations. And create memory kind operation is done by memkind create HMEM function. So the first argument is location of the mounted file system. Second argument is limit of heap because we create a fixed size heap. And third argument is input-output reference to dynamically created memory kind structure. So the heap management part is no different than presented in previous case. In 2019, Linux kernel version brings to the table Linux version 5.1, I believe, brings in support the volatile use of persistent memory as hot-blocked memory region functionality, which is called HMEM Dykes. Dykes as one of dev-Dykes described in persistent memory programming model. This was the blue line presented on the chart. When this feature is enabled, HMEM is seen as separate memory only NUMA node. Here is a view from memory topology system used by LS-Topo2. On this picture, HMEM configured as HMEM Dykes is presented here in the left bottom with 1 terabyte of memory and is placed on the socket 1. And we extend Memkind API to support this feature. Memkind allows automatic detection of and allocation from these new persistent memory NUMA nodes. And one of the additional values of Dykes HMEM is that supports copy on write mechanism internally. So here's the second example. In this example, we perform allocation to persistent memory using HMEM Dykes option. As you can see, there is no need to create kinds, so the kind management part is obsolete here. The code is simplified because this memory kind is presented as static memory kind. And what I would like to talk now about what we are doing now regarding Memkind. So inclusion of different types of addressable memory in package increases its overall complexity, and it's not straightforward to efficiently harness these capabilities. Currently with Memkind, we use only information about NUMA distance. This is a single data matrix provided by the hardware. However, NUMA distance doesn't fully correspond to memory performance characteristic. Heterogeneous memory like DRAM, high bandwidth memory, or persistent memory offers different performance characteristics. HMAT at speed table provides additional new information between two NUMA nodes, like read and write latency or read and write bandwidth between two NUMA nodes. And we properly HMAT supported in Memkind, we could better differentiate type of memory and that satisfy different requirements. We could use memory kind described as Memkind with memory with lowest possible latency, or memory with highest possible bandwidth, or memory with highest capacity. And about Memkind availability, we got support not only for C language, but also in Fortran and CPP. And regarding Fortran language, it is currently limited only to high bandwidth memory, but on our roadmap is to add support for PMM as well. As you can see, FastMem directive directs the runtime system to place this allocatable array A to high bandwidth memory. And about CPP, recently we added support for CPP allocators. Allocators are components which could be passed in STL container structure, and they are responsible for handling requests for allocation and deallocation of memory for a given container. So basically, this simplify possible usage of PMM in case of CPP library. So this is last but not least, let me talk about Heap manager features which are available in Memkind. Memkind internally tracks the kind of a given object from the allocation metadata. In other words, you don't have to remember from where you got your memory and keep extra metadata in your application. Memkind will handle detecting correct memory kind for you. This is presented on slide by passing a null pointer to freeing memory operation. Detecting memory kind from memory referenced by an address could be done explicitly as well. It is worth mentioning that using this functionality, we implicit using this functionality with implicitly detect kind comes with performance cost. So the cost is depending on application environment, is it multi-threaded or not, and how often these functions are called. Of course, this is a trade-off between simplicity of inclusion and achieving the best performance, but Memkind gives user the possibilities in this manner. So the second important feature is manipulate the heap manipulation. Despite the fact that real logic is handled by jmalloc allocator, Memkind provides a mechanism to manipulate the heap. So the Memkind hard memory environment variable, for example, is responsible to control if Memkind should release memory immediately to operating system or save it for reusing soon. Second option is Memkind background thread limit. To use, we could use this environment variable to use application background worker threads to asynchronously purge the memory. And third environment variable is allows to communicate with jmalloc itself. It basically we could use to manipulate the default number of gmalloc arenas, which is used by Libmemkind, and this got impact for memory usage and memory fragmentation. We could also use this function to tune up memory utilization, prioritize memory usage, or CPU utilization, depends of application requirements. And that will be pretty all. So here are a couple of useful links. First one is a link to Libmemkind repository. Second one is a link to persistent memory, which includes description of persistent memory development kit, already mentioned it in my presentation. And the third one is my email. So if anybody got a question, I will be glad to answer for some of them.
Okay, excellent presentation. Thank you very much, Michal. And sorry for not introducing you at the beginning of the slide. So thank you so much, Michal Biesek. So questions from the attendees or the rest of the panelists? If any attendee has a question, feel free to raise your hand and we will give you permission to speak. So in the meantime, I take the opportunity to ask you, Michal, in the context that any other vendor is willing to provide any different kind of heterogeneous memory, would that be difficult for Libmemkind to adopt it?
From Libmemkind, not, but we must remember that as I already presented on the slide, sorry to interrupt, that if you see that one of the, to achieve the best performance, let's say one of the requirements of this medium is to support this Dykes option, which I already mentioned, to omit the page cache mechanism. But from Libmemkind perspective, if it is presented as, basically from Libmemkind perspective, the first example related only to fact that this should be presented as block mounted device. So if it's presented as file system, it's fine for Libmemkind.
Okay, cool, thanks. So I understand that we need that any other vendor to implement this part of the kernel space functions so that Libmemkind can adopt it. Okay, it's fair, I believe. Okay, we have a question from the attendees. Let me see. Oh, where here. Siddharth, please go ahead.
Hello.
Hello.
Hi, this is Siddharth from EPFL. My question was, does Libmemkind provide, like right now, or is there going to be support for migrating pages between these different memory devices?
Yeah, that's a good question. So currently, Libmemkind doesn't support this functionality, but what I could highly recommend is to read more about separate functionality provided by, I believe, newest Linux kernel called HMEM. Basically, okay, so from Libmemkind perspective, it's hard to track the information which data is hot and which data is cold. And with HMEM functionality, which is a separate functionality, it internally tracks the aspect of hotness or coldness of page, and moving the data to corresponding medium from its internal measurements. So, but to answer your question, Libmemkind currently doesn't provide, let's say, moving pages from between memory kinds.
Okay, thank you.
So we have a question on the chat box. Ed Geringer asked, can you say something about address mapping? Is there a single address space for all types of memory?
So basically from the okay, so how to not sure. Persistent memory and high bandwidth memory operates on the same address memory space as DRAM. Basically, it is presented from the OS perspective as NUMA nodes. So not sure if I answered your question.
So Ed, I can give you voice. Ed?
Yes. Okay. I mean, that's a start at an answer. You know, I think these probably can be configured in different ways, but I'm just, if you have persistent memory in the same address space with the memory of the running process, then address space management is going to start to get a little complicated.
Why?
Because the process is, I mean, unless the whole system is in a single large virtual address space at all times. Otherwise, when a process starts up, it's going to have a virtual address space that starts as 0. And you know, and it's going to have its own 0, and another process is going to have its 0. And all of these different blocks need to be mapped into a single large address space. So there needs to be some translation going back and forth, because otherwise the processes are not going to be able to use their, you know, their virtual memory starting at 0.
Yeah, but basically it is, let's say, handled by kernel part, right? So okay, so let's say currently updirect mode, it's already used by some mediums, and the part regarding handling correctly the address space is, let's say, in a manner of this kind of libraries like PMDK or Memkind. So basically, it's, from my perspective, it's transparent for application.
Okay, we're over time, so thank you for that answer. That helps.
Okay, great, thanks.
Okay, thank you. So please, if there's any other question, feel free to, well, if Michal wants, send questions to Michal around Memkind. So next presenter is Marc Jordà from Barcelona Supercomputing Center. He will present an ecosystem of tools for broad heterogeneous memory usage. So Marc, ground is yours. Marc? Yeah, I can unmute you. And I think you can also unmute yourself, don't you? Or how does it go? Sorry, I'm a noob on this. Oh.
Yeah, I didn't have the button. I interfered.
Okay,
when
sorry.
When you unmute, then it asked me to unmute.
Ah, okay. Good. Sorry, I'm
me...
completely noob on Zoom.
No problem. Can you see my slides?
I can, yes.
Let me see, one moment. So, can you see it properly? So, well, yeah, my name is Marc Jordà. Thanks for joining this afternoon. I'm a research engineer at Biesek, and I'll present the work we have been doing, or we are currently doing, in collaboration with Intel related to automatic data placement in heterogeneous memory systems. In this case, well, just a short summary, it's basically a set of tools and libraries that allow us to enable applications to use the different memory tiers in a heterogeneous memory system without changing the application itself. It's done via interposition and profiling. I'll show you more. So Usually in computing, when we talk about heterogeneous systems, we usually refer to the processing heterogeneity. They have been here for long, and I would say almost any system now in HPC is heterogeneous. Usually it's system with the CPU and some other computing element, usually an accelerator, GPUs, KNLs, FPGAs also, etc., etc., etc. There's even the, let's say, the heterogeneous processors that have like different types of cores, like would be the ARM big little, but those are not that much deployed. But there's also another type of heterogeneity, that the one that we are interested in, which is memory heterogeneity. And especially in the recent years, it's memory technologies or other memories in the systems that can be managed by software, okay? Which open the possibility to new, let's say, things. Some examples of memory heterogeneous types of memory. Well, we have scratch pads, for example, in the GPU, have a shared memory, or embedded processors, DSPs, have a scratch pad for a long time, which are the small cache-like but software managed. Then in terms of new technologies, we have the high bandwidth memory that's used in GPUs and was used in the KNL. But it's true that this type of memory usually replaces DDR, so it doesn't create a heterogeneous memory system. It's a replacement. Finally, let's say the newest technology, or one of the more recent, is the commercial products based on non-volatile RAM memory, or it could be Intel obtained products based on the crosspoint technology, which they do create an heterogeneous memory system in the sense that you have DRAM and you have the Optane that you can use to allocate your data explicitly. And we think that this trend will continue in the future. Basically, because the idea with heterogeneity is that different types of memories or different technologies offer different features. Here in this picture, we have, let's say, a hierarchy of what are these memories. The thing is, there's features, usually there's the typical capacity versus latency advantage or features, but then there are others that we'll see. We start closer to the CPUs, we have the usual caches, we have the scratchpad, like cache-like speeds, small like caches, but software managed. Then in between the caches and the DRAM, there is some systems that have this on-chip DRAM cache, like with the MCDRAM in the KNL, which basically is another tier in between, or another level in the speed versus capacity hierarchy. Then on the RAM side, it's these 4 boxes here. RAM would be the normal DDR, but then we have like specialized type of DDR, like low power DDR used in mobile phones, ECC enabled DDR for, let's say, critical systems that cannot afford memory errors, and even like the memory types specialized for some type of access. In this case, for example, GDDR used in GPUs, where you can exploit the higher bandwidth, taking bigger contiguous chunks. And then in between this DRAM level and the disk, which is not pictured, there's the NVRAM, the non-volatile, the PMM thing, which is, as Michal talked in the previous presentation, another level that gives us, let's say, capacity is way higher than DRAM, but at slower and reduced bandwidth, but much faster than disk. In our work, what we advocate is, let's say, to fully exploit the heterogeneous memory, these software managed memories that are appearing in or are available in newer systems, is to move, let's say, to make these different memory tiers first-class citizens, and try to move from the classic approach, which would be the picture on the left, where you have this hierarchy where the small fast memories are caches for the not so fast larger memories, and try to go to a scheme or a model pictured on the right, where there are several software managed memories, and the software, whoever it is, the software can try to use these memories in a smarter way. Moving from the typical model to this model opens a lot of questions, because what the hardware used to do now is open for the software. So it is who manages, or decides where data goes, or who manages each memory. Could be the OS, could be the application, could be a middleware, which heuristics to use, if the placement should be static, should be dynamic on the fly, using counters, etc., etc., etc. The idea is that moving to this model, it opens the need or the possibility to develop and research on tools, libraries, rented systems, profilers, to make this easier for the application developer to exploit these different memory tiers in ways different than the typical approach. Focusing more on the available memory or heterogeneous memory systems closer to what we use in our work. Scatterpaths, let's say, are too small for what we need. The first one would be the KNL. I mean, Michal already kind of presented this a bit. There will be some sort of follow-up. I'll try to go fast. But the idea is that KNL, well, it's discontinued already, but there's systems that have it. The idea is that you had the DRAM, you had the MCD RAM, it has higher bandwidth, higher latency. The idea is that you can play with it if you want. The same happens for the Intel Optane DC, the memory DIMMs. The idea is to go from a system which has only one memory tier, which would be this picture where all the memory objects are there, to a model where you have several memory tiers. On this example, there's 3, and you can place different objects in different places. And the goal here is try to find a distribution that fits some needs. For example, maximize performance or keep performance similar to some other system, or try to minimize energy, or whatever metric do you target. Usually, yeah, when we talk about heterogeneous memory in our group, I don't think, yeah, it's not a, let's say, widely spread distinction. We try to distinguish deep memory from a heterogeneous memory. The idea is that deep memory would be this classical hierarchical model where it's the smaller caches for the larger memories. And heterogeneous memory, in our sense, is this model of having the software managed memory tiers as first-class citizens. There's nothing wrong with the deep memory. It's pretty good for high locality scenarios, but it's being usually hardware managed, is kind of limited to what the hardware can do. The other type is managed by software, so you can implement fancier things, let's say, or try to exploit them better for your target. Another option or another question that opens up when you want to manage the memory tiers explicitly is at which object granularity should you work. And the two that come in it, it's these two, page level or allocation level. Page level would be the more the operating system view of memory, and in this case, it's good in the sense that you can exploit already existing code in operating systems in terms of migrations or tracking or swapping to disk or other memory tiers, etc., etc., etc. But it's true that you kind of miss some information that if you can use if you work at the application level. Because let's say in the application level, yeah, an object could be a variable or a malloc allocation, which is the one that we use in our work. We work at the application level. The idea is that, for example, you can assume that pages from the same allocation will have the same behavior. So you can treat them like the same, and you don't have to handle each page individually. And also, if need be, you can even use some feedback from the users. Focusing on the Optane DIMMs, which systems with Optane DIMMs, which is the one that we present evaluation for. The idea is that you have normal DRAM memory and also some DIMMs that are from persistent memory. We don't use the persistency part. We use the fact that they are byte addressable and offer another memory tier. For us, they are high capacity. You have DIMMs up to 512 gigabytes. So it's like more than an order of magnitude. But they do have drawbacks, which is they have higher latencies and a smaller bandwidth, even though they are much faster than SSDs. They are in between. As Michal introduced, there are two modes. The UpDirect mode is the explicit mode where you have the DRAM as the normal DRAM, and then you have the Optane DIMMs that you use through the Dykes devices, which is the mode we use in our framework to place the objects. And then there is the memory mode. We also call it cache mode because of the kernel. The idea is that the DRAM acts as a cache, hardware cache for the Optanes, and the system doesn't even know it's there. The memory controllers do that for you. And what the system sees as the main memory is the Optane DIMMs memory. And that's what we use as our baseline to evaluate our framework. And yeah, in a direct mode, well, normal mallocs go to DRAM, and then you have to use special libraries to allocate on obtain. In this case, well, Memkind that Michal introduced pretty well. So the idea is that you have a similar API, and you can allocate from different memories. So for the framework itself, the idea is that what we do is automatic data placement at the application level without changes in the application. And we work with objects as heap malloc allocations, heap allocations. And it's basically an offline model and composed of 3 steps. There's the first step where we take the application, we run it with a memory profiler. In this case, we use Extrai, which is a tool from BSc profiling. And from this profiling, first profiling execution, we collect data on the dynamic memory allocations, their size, etc. And also we collect some hardware counters related to the cache behaviors, especially as low cache, but sometimes also L1s, which mainly, yeah, normal counters. And we also collect sample PEPs counters, because PEPs counters, these precise counters, not only gives us the amount of misses or hits, they also can give us which addresses were being accessed when there is a miss. And with this memory, with this profiling data, we feed this to the HMEM advisor, which is the program that, using this data, uses some heuristics, some approximations, tries to model or decide which objects, which allocations are more sensitive to latency and bandwidth and should go to DRAM, and which objects are less sensitive, usually are the ones that, yeah, when the DRAM is full, the rest go to PMEM. And once we have this object distribution, we run the application binary without any modification. Again, we load a library which is called FlexMalloc. It's an interposition library that interposes the normal malloc calls and malloc and the whole family of functions. And using the object distribution that the HMEM advisor generated, it diverts or puts the data where it should go. And the application does not realize about that. The application is still using normal mallocs. And well, just to mention, this is, let's say, a continuation of the work that Tony was doing in Argonne. So for the experimental evaluation, well, the hardware platform that we use is a platform with 2 Xeon Platinum CPUs. Well, yeah, usually hardware thread disable. In this experiment, I will show we use single socket executions. This is a thing we do to control the amount of cache, of DRAM cache in the memory mode, because each socket, the caching goes independently. So if we pin to one socket, we know that we can control the cache size to 16 gigabytes. We have, yeah, in this configuration, 60 gigabytes of DRAM per socket, and well, 3 terabytes per socket of the tail, even though we don't use as much. In terms of storage stack, we use, well, Intel compiler suite, Intel MPI, and yeah, the machine runs Fedora 27. So here are some results with mini apps, HPC mini apps. Basically, in these plots, you see in the y-axis is the figure of merit of each app. Yeah, in all of them, higher is better. Then each cluster is the data we use to decide, or the HMEM advisor uses to decide which objects should go where. We have different configurations. That's each cluster, and each color is the amount of DRAM that we allow the HMEM advisor to use. And the following execution with FlexMalloc. The cache mode baseline is the blue line that you see in all of them, is always with 16 gigabytes. Okay. So we start with, let's say, with mini FE, which is the one that gives us, let's say, better results. You see that, you can see that almost any configuration we have, yeah, close to 2x speed up without, yeah, even with executions when we only allow our framework to use 1/4 of the DRAM that the cache mode uses, the memory mode uses. Then we have HPCG, which is not as good in the sense. It's true that we are always close or better than the baseline, but we see that, for example, it has an impact when we use only load information to decide which jobs are important, or we use loads and stores. And also you can see that giving more DRAM, which is what we would expect to our executions with our libraries, it also increases the performance, and we can get up to 2x also for the green column in the middle. But then for a few of the mini apps, those are not that good. I mean, we do have, let's say, comparing fairly, like if the cache is 16 gigabytes, we should consider only the fair comparison would be with the green columns. With one of them is close to the performance, but the other have some issues. This is, well, there are some pathological cases that don't go well with the heuristics that we use to classify the objects. And also just to know that the results are not with the latest version of the advisor. We improved the algorithm recently because we had some cases where we had some under occupation of DRAM, and we had to do some changes. So this may improve in the final numbers. And then we also, besides the mini apps, we have also results for full applications. In this case, LAMS, which is a molecular dynamics simulation, and OpenFOAM, which is fluid dynamics simulation. In the case of LAMS, this is slowdown versus the baseline with 16 gigabytes, the cache mode, and each column is the RAM that we allow to use in our framework. You see that the three of them are very close to the baseline, it's just a few percentage points. The interesting part here is that, similar to with mini-FE, giving 1/4 of the memory to our framework, we can get similar performance than the memory mode. For the case of OpenFOAM, we are still finishing to get the last numbers. These are results for 16 gigabytes. So yeah, it's comparing 16 gigabytes in our framework with 16 gigabytes in the cache. And each column here is our executions with different execution times. We allow the simulation to be longer. So as you can see, yeah, with very short simulations, we are close to the baseline. But then when we get to more realistic simulations, like 1.5 hours or 3 hours, we see that we get a decent speed up in this case of up to 18%. We plan, yeah, to try larger cases. So to summarize, heterogeneous here to stay. I mean, we've been having computer heterogeneous since long before, but the idea is to point out that it's not only processing heterogeneity that's important or that's available, there's also memory heterogeneity, and especially now that it's software managed memory that you can control from the software side. And maybe in the future we'll have other types of interesting heterogeneity. The idea here is that as it is now, there's different APIs to use this memory, either Memkind, either the ones implemented in the kernel that Michal commented. But the idea is that there's not much smartness yet, so there's an open research possibility here to try to use like either kernel level or middleware or application level automatic and guided data placement. For our work, well, we develop this ecosystem of tools and libraries. What we use is UpDirect, and the idea is that use these memories in a more efficient way and try to be, let's say, closer with less DRAM to the hardware approach, the memory mode, or get some speed ups when we use the same amount of DRAM in the cache mode and the memory mode. We're working on a paper on this, and also we'll release the software as open source at some point. We're working on it. So hopefully in the following weeks, there'll be some updates in the website here. Some acknowledgements on the team, well, Antonio, well, some former employees, Muhammad, that's not here, Jesus, and also the colleagues from Intel, Harald, Servat, and Marie-Christine Soli. Project acknowledgements, the Intel BSc collaboration, and also the EPIC project from the European Horizon 2020 research. And that would be it. If you have any question now or later on, you can send me an email.
Thank you, Marc. That's a great talk. As we said, we will prioritize questions made live. So please, whoever has a question, raise your hand. And in the meantime, let me ask you some questions that there were in the Q&A box. One question that was, some questions have already been, were more like for Intel employees, so they have been answered. There are some left for you. Gaurav Cole from HPE said, how about NVIDIA GPUs as well as a model as they use HBM a la MCD-RAM, or is the focus on CPU general purpose only?
So far we used on CPU only. It's true that the model is, I mean, it's generic in a way, but we didn't enter on the heterogeneous compute part yet. The idea was like, okay, let's say focus on the CPU and work on the different memory tiers that we have available there. This can be extended. The thing is, if you mix GPUs, things get more complex. The heuristics probably get more complex also. It's different, the characteristics of GPU allocations or CPU allocations, how do they affect the performance. I mean, it's all, it's open for research, but we didn't tackle that, at least yet.
Okay, so I see no more hands raised. Please, I remind you to raise your hand if you want to ask something live, which we prefer. I'm gonna ask you other question from the Q&A box. From Sergey Vinogradov, do you have two different source branches in the code for cases with heterogeneous memory and without it?
No, the application is not modified in any way, if that's the question. The idea is that we use this offline profiling approach to get the data that we need to know which objects should go to decide the distribution, and then you can run the application with interpolation library that will automatically place the objects in the different places, in the different memory tiers. But the applications are not modified.
Okay, thanks. One more question in the Q&A. Thanks, this is from Mario Marino. Thanks, what is the part of the infrastructure that is causing large overhead?
Well, there's several, no, it's not large overhead. The idea is that since we use profiling information to decide which objects should go where, you cannot always get, I mean, you don't get like an idea or oracle. For example, we rely a lot on PEBs, and PEBs usually it's sampled, so you get, let's say, one miss every whatever misses that you configure. So depending on the access pattern of the application, the data that you collect may not be as representative as you would want to make a proper distribution. Because then we use this data. The thing with PEBs is, since it gives us information on the addresses that it's accessing, we can map this with the allocations and know which allocations, or try to decide which allocations should go where. And yeah, these heuristics have several parameters, and it's hard to find a heuristic that works with all the cases.
Okay, thanks, Marc. I see no more questions. Last chance for questions for Marc. Okay, then thank you very much, Marc. Let's move to the next speaker right on time. Next speaker will be Dykes from HPE, and his talk is Abstractions for Data Management in Heterogeneous Systems. Tim, let me, okay, great, go ahead.
Can you hear me?
Yes.
Great, so I'll just share my screen here. Okay, can you see the screen?
We can, great, thank you, go ahead.
Okay, fantastic, so I'll get started. So hi everyone, my name's Tim Dykes, and I'm going to talk to you today about abstractions for data management in heterogeneous systems. And a quick background about myself. I'm based in the HPC and AI EMEA Research Lab, formerly part of Cray, and now part of Hewlett Packard Enterprise after the recent merger. We're a 12-member team split across Switzerland and the UK. I myself am based in Bristol in the UK. And we focus on technical collaborations with customers, centers of excellence, this type of thing, as well as joint research ventures with both customers and non-customers. So I have some of the projects that we're involved in here on the slide. And we don't work specifically on sort of Cray or HPE products, but try to understand what products of the future should be and understand real customer problems and interact with them on these. And so one of my roles is work package leader for the memory work package in the Epigram HS Horizon 2020 project. And it's the work that we're doing in this work package that I'm going to speak to you today about. And in general, my background, I have a doctorate from the University of Portsmouth in the UK in high performance computing, visualization and astronomy. And I'm interested in these heterogeneous architectures, optimization, application coupling, and graphics and visualization. So Epigram HS is a Horizon 2020 project focused on enabling extreme scale applications on heterogeneous hardware. And so what I mean by this is we're looking at sort of traditional high performance computing applications, might be written in Fortran, C, using things like MPI, and then looking at heterogeneous systems and the wealth of software and hardware environments that are available to take advantage of in sort of a modern heterogeneous high performance computing system. And the project itself is split into three sort of components: network, memory, and compute. So the network component is focusing on MPI and GASP, so extending these proven technologies for heterogeneous hardware. And compute are focusing on runtime and DSL for FPGA programming. I'm going to speak today about the abstract memory device model we're developing. And we're doing this work in the context of a few pilot applications, including weather forecasting, space weather, CFD, and some AI use cases as well. So to motivate this work, I thought I'd like to make this comparison between sort of an original, an early Cray 1 versus the current day recent top #1 in the top 500 list, Fugaku, and sort of compare the performances. And so we can see that sort of in general floating point performance, we really have orders of magnitude, increase, which is, expected over the years since the early Crays. And this is, the same per node. We have orders of magnitude increase, memory capacity, and memory bandwidth per node. But memory bandwidth per flop is actually quite a lot lower than it used to be. And, this is, of course, due to the limitations in memory performance. But I think this quite well highlights that our memory performance is not able to scale as quickly or as widely as our computational performance. And while this isn't quite the whole story, it does sort of give rise to these complexities that we see in the modern memory hierarchy. So this, we're talking about many different layers in your memory hierarchy, each with their different sizes that you need to consider, different characteristics, speed versus latency, et cetera, et cetera. Each of those may have their own vendor APIs. They may or may not be integrated with modern programming models. You may need to use these explicitly, or they may be used under the hood by existing runtimes, drivers, this type of thing. I need to consider how you transport data through this hierarchy, how you may redistribute your data to be best utilized for the memory that it's in, or the type of device that's being used to process it. And then the additional costs with porting codes, the longevity of your code when the hardware and software is evolving so fast, and many other problems. And these are sort of the motivators for our work in Epigram HS. And so I'm going to describe our approach, which is really focusing on how So modern exascale applications might be able to use a variety of memory systems easily with good performance, requiring minimal code intrusion and in a measurable way. And I'm going to talk about a library we've been developing called the Mamba library. And this library is focused on managed abstract memory arrays, forming a sort of lightweight wrapper around user data. And these four layers summarize the sort of core focuses of this library. You know, at the top level, we have programming model and language support. How do we integrate with either the language or the programming model that the user might be exploiting in their application? And then providing a set of data management abstractions that they can use to manage the application data, supporting this with a generic memory allocator that's able to allocate and move memory across a variety of hardware and software. So the abstract memory model that we're talking about here is sort of the assumption that you have a variety of types of memory on a single node with different characteristics. And we group these together into an abstract memory space for use in an application. And so you might have, a fast memory, working memory, and a large memory that we group together and then allow the user to access, typically via a Mamba array object. In our library, this is what our abstract memory model looks like. So we have a resource manager and a set of memory layers. And so a memory layer is a particular type of memory with a well-defined set of characteristics. The user is then able to create a memory space, which is a size-limited, addressable instantiation of a specific layer. They then acquire a memory interface, which allows you to allocate blocks of memory out of that space, and the blocks of memory come in the form of allocations. And then we have what's called an execution space, which determines how memory should be allocated and how it should be made available. And so this allows you to customize the way your allocator allocates memory and how it's structured to be available in the programming model that you might be using. So a general approach for memory management then, based on this memory model, is that the user will explicitly or implicitly register or discover available memory. So on the one hand, if we don't know anything about your memory system, then you should tell us which layers you might have available such that we can allocate from them. On the other hand, if you build the library with HWLock support, then we can discover the available memories seen by HWLock and then automatically build this memory model and provide spaces for you. The user then request a memory space for a specific layer, request an interface to that space, and then either allocate memory explicitly and do what they wish with it, or they can then construct a Mamba array and have sort of a more high-level view and some interesting features which I'll discuss. So the concept of a Mamba array is that it may inherently be spread across multiple memories. So Mamba array may consist of several tiles, and these tiles may be duplicated or moved between the different layers of your memory space. And that movement may be controlled explicitly by the user or implicitly by the Mamba runtime. And these can either be self-allocated, so Mamba can do the allocation for you, or if you already have an existing allocation, that can be passed in and we can wrap around it and incorporate it into our memory model. The concept of an array layout maps our Mamba array indices to physical memory. And so this describes the characteristics of our array, dimensionality, what our array elements look like, are they simple or structured, what type of ordering scheme you may have for your indices, what type of layout you may have, so sort of simple linear versus block cyclic or sort of more weird irregular layouts. Padding, pre and post dimensional padding, this type of thing. And so we use this sort of abstraction for copying, writing, and accessing tiles in the Mamba array. And so the Mamba array tiling is a decomposition of our array into tiles. And these could be known as chunks, blocks, pieces, subsets, whatever. We use the term tiles. in this library, and it's based on initially a user-provided tile size, although I'll talk more about that later. And then tiles may be accessed either by index in the tiling scheme, or they may be iterated over via an iterator object, which has an inbuilt schedule over your tiling. And then those tiles might be duplicated or migrated to alternative tiers of memory with individual elements accessed using indexing macros. And I'll show some examples of what you can do there shortly. So just to give you an idea of what we mean when we say duplicating and migrating tiles, we have this process of either duplicating an array tile to another memory, i.e. you have 2 copies of a particular tile of your array, and while only one is legally accessible, you may then merge it back into the parent tile once you're done. And then we have the concept of migration, where you actually move your array tile to a different memory space, and the array is then inherently spread across spaces. And the user can choose to duplicate or migrate using our API, or during tile iteration, the runtime may internally duplicate or migrate if we believe it's would be reasonable to do so. And then we optimize this through what's called an access type and merge policy. So the access type is how you expect to access your tiles. You could duplicate an array tile as a read-only object, and then we might be able to put it in some faster read-only memory, for example. And then the merge policy defines how your tile data gets copied back to its original place. Maybe it's just an overwriting, or maybe you need a function that merges your array tile with its previous version in a particular way. And so then metadata of the tile is made available in the expected execution space. I'll show you how the API works for this. So that, once a tile is in, say, GPU memory, you can actually access the information about that tile once you're there. So people are often, application developers, one of their major concerns is often, how do I access these tiles? Is it going to be performant? Is it going to vectorize? So just to give you an overview of how we allow users to access the tiles of their array. They have tile accessors via either index or iterator. So you can either access a specific index of your tiling, or you can ask for an iterator and use normal iterator operations. And then we have a few different ways of accessing the actual tile data. Here we have sort of preprocessor convenience macros for array indexing. You can also have a getter for the pointer, which you can then index manually, either using an index expression macro, which we provide, or writing your own index if you have knowledge of the tile layers itself. And so this is the approach we're using for the C version of the library. Our initial implementations are in C and Fortran, with a C++ implementation to follow. And we expect that initially the C++ version can replicate the C approach, but we really would like to use some more advanced features of C++ to simplify some of this API, which it can be as it uses the limitations in C. The use of preprocessing macros, etc., is sort of required here. But in C++, you might template your tile on the array type, so you don't have to do things like tell us what type your pointer is. And we're looking to investigate how we can use C++ meta programming to ease this API usage. So it's something like you might see in Cocos, etc. But there are initial implementations in C and in Fortran, where we can either replicate the C API approach with linear indexing, or you can also use sort of multi-dimensional Fortran objects where you request a tile, an n-dimensional tile pointer for contiguous data, or for non-contiguous data, where in some cases we can use sort of Fortran array slicing notation to represent these. And as I said, application developers typically want to know what's going to vectorize and what's not. So just as an example of what we've been exploring is how our our array indexing methods might or might not affect vectorization. And so there's a lot of information here, just a quick overview that, you know, there's a variety of types of indexing that some might think might not be vectorized, others might expect this, but you know, when you don't know exactly how long your array is going to be, so runtime defined flat indexing, you know, all of these types of things typically do vectorize, and then it's only when you start moving to sort of non-inlineable functions where you can do really advanced indexing where vectorization starts becoming difficult. And so this is one of the focuses of our work, is to understand at what point do we, how complex can we make a layout while retaining sort of vectorized access? And when it becomes too complex, then how can we restructure our array layouts sort of implicitly such that you can have a normal indexing scheme that will perform well. So I'll show a quick API example of array tiling with duplication on the GPU. So we initialize our Mamba library here. And this is built with HW lock support. So in the background, a set of memory spaces are created. And so we can simply request a DRAM-based memory space with the default execution context for DRAM, which will be just on the CPU. No configuration options, but here you might add some configuration like a size limit or something like that. Default sort of interface options. We then request an interface to this space and start constructing our Mamba array. So we have a constructor for a regular 1D layout with the size of float as our element size, no padding. So the simplest layout you can create. And then we construct an array based on this. So first the dimensions of the array, our layout, the interface that should be used to allocate this array object, and an access type. So we say we want this array to be read-write. And so we have just a non-Mamba function. I don't show this, just sort of initialization of the array data so that the rest of the example makes sense. Now we want to we want to tile our array, loop over those tiles and duplicate them in GPU memory so that we can do some processing on the GPU. And so this is how we might do this. First, we request a different space and interface. So the API is the same, but it's GPU memory now. And we ask for an interface to the GPU memory space. We then go into tile array, which is called MBA. So we choose a tile size. Again, it's only in 1D. The 2D, you know, if it was a 2D array, it looks the same, but you have two chunk dimensions instead of one. And then we're going to loop over the tiles. And so when using indexed access like this, it's a little more verbose. Tile iterators can do this in a slightly less verbose manner, but I show this one as sort of more intuitive. So firstly, we create a couple of objects, check the dimensions of our tiling, and then iterate over all of the tiles in our array tiling. We request a tile of our array at this specific index, and then we duplicate that tile on the GPU. So we say, we pass in our tile, the new interface to allocate memory for this duplicated tile, a new access type, a layout. In this case, we use the same layout, so we're not changing layout, but you may put a different layout here, in which case there'll be a sort of implicit transformation underneath. And then you get back a duplicate tile. And this duplicate tile is the information about the tile, the metadata is available on the CPU initially, while the underlying data is allocated on the GPU. And so we do this thing called getting a space local handle, which gives us a device version of that tile that we can actually, you know, pass off into a CUDA kernel, and it'll be, all the metadata will be accessible on the GPU. And so our CUDA kernel runs, does some processing on this duplicate tile, and then we merge it, which means merge it back into the parent tile it came from with an overwrite strategy. So we're just replacing all of the data that was there originally. So to summarize the sort of high-level capabilities of this library we've been building, our prototype allows the programmer to allocate arrays across heterogeneous memories. We initially have supported DRAM and GPU for our prototype. provided tiling support, which allows you to split your array into trunks and use our API to transport this across layers using this duplication and merging setup. We have some layouts supported, sort of regular up to n dimensions, block cyclic, and some layout transformations. So you can create a block cyclic array and then create regular layout tiles from this for access. And we're developing this in a private repository at the moment, but over the next few months, our main focus is now early benchmarking with our partners, extending our initial framework to support a wider range of supported memories. So, start looking at flash, storage, remote memory, this type of thing. Widen our range of supported execution contexts. So currently you can access a tile in your CUDA kernel or in the CPU. But if you want it to sort of be natively accessible in an OpenACC context or integrate with OpenMP, HIP, this type of thing, that's what we're working on at the moment. We're looking at optimized/overlapped data transformation and movement approaches and how we might distribute these arrays across a multi-node memory hierarchy. And this will end up open source by the end of the project. So I sort of expect in the next 6 months that we'll be in a position to make this open source and start getting some more community feedback outside of the Epigram consortium. And so our proposed usage scenarios where we think this library would be useful is firstly addressing and evaluating multiple memory types with minimal code change. It's a non-zero amount of code change, so we do expect that the user is willing to experiment a bit, but we hope this will allow them to evaluate a wider range of memories with less experimental code than they would have required before. You can then use this approach for things like staging or blocking through multiple levels of your hierarchy, overlapping offload to accelerators. So duplicating a tile in the background while processing another tile, to automatically splitting your data to offload to multiple accelerators per node, and restructuring, redistributing, and reusing your data for optimization purposes. And so internally, we're developing a set of benchmarks. We're also using the Rodinia benchmarks and working with our partners to implement sort of library usage in the demonstrator applications, which include the escape dwarfs for the IFS weather code, along with IPIC3D and NEC 5000. And then this the framework we've built so far and now allows us to sort of answer a few interesting research questions. And so what we're really focusing on is, what kind of implicit optimizations can we do based on this tiling abstraction? So if you have a tile iterator with a defined schedule, what can we do on the runtime side for resizing your tiles or deciding where and when they should be moved based on memory characteristics? And so we have our partners EPCC are doing some work on cost modeling for this type of optimization. We're very interested in how we might automatically tile your code via compiler extensions rather than explicit use of this API. And so we're sort of exploring how the user might provide directives instead of API usage, and then we use the tooling interfaces to our Clang and the new F18 or the new Flang, Fortran front end in LLVM to insert tiling for you, as well as exploiting sort of polyhedral frameworks such as ISL and PET for optimization analysis and understanding when a tiling is valid and when it might be beneficial. And one of the things we're starting to look at, but it's not been a major focus, is whether this framework would be useful for FPGA development as well, and how we might support sort of more advanced features such as hierarchical tiling, how best to support halo regions and things like mixed precision transformations. So duplicating a tile in a different precision than it was before to transport to an accelerated device. And so thanks very much for listening. Funding for this work is the H2020 project, so acknowledgement here along with the partners that we're working with in the Epigram HS consortium. My email address here for if you want to contact me, and happy to take any questions. Thanks very much for listening.
Good. Thank you so much, Tim, for your presentation. Quite inspiring. So I have some questions, but there's a question from Q&A. I wonder if David Strelak would like to go live. So I'm allowing to talk to him because I wonder if he would like to raise the question live.
Yeah, sure.
David, I allow you to talk. Could you?
I see his, he says his microphone doesn't work at the moment, but I see his question.
Okay, so yeah, his question is, can or does the tiling in Mamba lead to wasting memory?
And so, of course, whenever you're, duplicating memory like this, there's a possibility for wastage. Our implementation, we aim to reduce the amount of memory the library uses internally. But when we provide the user with a means of duplicating tiles in alternate tiers, then there is the possibility that they might duplicate more than is needed. And of course, if you have multiple copies of your data, say one on the CPU and one on the GPU, then it can be difficult to know how long to keep these around. So, it's not always clear whether the user is finished with a particular block of memory and you might need to keep it around. And so, there is the possibility for more memory than is necessary to be used, but we try to provide a very sort of lightweight wrapper on the user memory so that they still have quite a sort of firm control on how it's managed. And we aim to reduce sort of the opportunity for wastage as much as possible.
Okay, good. So we have some time for further questions. If some of the attendees have questions, feel free to raise your hand. I have some questions on my own. First one is, I wonder if you could briefly compare your approach to what OpenMP5 brought us when it was released.
Yeah.
So how does Mamba and OpenMP5 compare with respect to the memory allocators?
Yeah, and so if I skip back in my slides here to our abstract memory model, and this is actually very similar. And so, I mean, if you try to come up with an abstract memory model with a generic memory allocator, you often end up with something that looks like this. And so the OpenMP5 spec for memory allocation looks a little bit like this. Cocos looks a little bit like this. And so what we hope is that the similarity means that where sort of interoperability becomes very easy, such that you might already have used the OpenMP memory API to allocate your memory, but then you could wrap Mamba array around that and use our tiling abstraction to then manage that memory afterwards. And so sort of we hope that there is enough similarity to make this quite easy. And as I mentioned, our sort of first support was on CUDA and the CPU. Our next steps, which we're focusing on at the moment, is both OpenACC and OpenMP support. So really ensuring that they're as interoperable as they can be, because we don't want to replace the programming model. We want to be we want to add to it and help you manage your memory without we don't manage your parallelism for you, this type of thing. And so we focus purely on the memory hierarchy.
Okay, good. We have Siddharth, who has raised his hand. Let me allow him to talk. Sid, I unmuted you also. Sid, I think that you have to accept being unmuted.
Can you hear me?
Yes.
Yes. So I have a question on granularity on the tile size. The question is that given the tile size is decided by the user, do you have any suggestion for optimal deciding on optimal tile size?
So we have two approaches. One is that the user can sort of manually schedule the data placement using the API example that I showed. And the second approach is the this sort of automatic approach where we use a tile iterator object, provide a schedule of tiles, so we know how the user plans to pass through the data, and then we this to decide the optimal placement of that data. We have a partner who's working on sort of cost modeling approaches.
Okay. There's no question I want to ask about tile duplication. Is duplication is copy and write or copy and duplicate?
Sorry, I didn't quite catch that.
Me neither. Can you repeat?
So when you duplicate the tile, do you make a copy when data is written again, or you make a copy when you duplicate right away?
So the duplicate is a copy, exactly that.
Okay.
And we use the term duplicate to differentiate from the term migrate, which is move. So in both cases, you have to copy the data, but in the migrate case, it means we might be free to reuse the original place. But duplicate, you assume that at some point you will be moving the data back where it came from. And so this is sort of there's multi-levels to that. So, you might have your array that's actually entirely in storage and duplicate a tile into DRAM and then duplicate the tile into, your accelerator memory from there. And then merge this back into DRAM and merge that back into storage.
Okay, thanks.
Good. So we have two more questions, Tim. Is it okay for you to take them?
Yeah, absolutely.
Good. So let's go in order on how they appear. So Run Vinci asked on the question and answer. Do you plan automatically scheduling the data to physical in memories, or let the user decide? If so, which model will the scheduling algorithm be based on? And thanks for the talk, by the way.
So I think I sort of partially answered this in the last question. As I said, there's sort of two approaches. One of them is allowing the user to make these decisions using the API example. If I just skip to it quickly. At this API example, so allowing the user to explicitly call these duplicate functions and put the data in the physical memories that they want it to be in. And then our sort of research project is how can we automatically schedule this? So if we use a tile iterator object with an inbuilt schedule over tiles, when should we duplicate them? And what's the optimal way? Should we restructure them as we duplicate this type of thing? These are all the questions that we're trying to answer in this project. And so I don't sort of have an answer for which model will the scheduling algorithm will be based on, but it's something us and our partners are working on in this project. Yeah.
Okay, so last question. It's from Hatem El Shatli from Biesek. So I'm allowing him or her to talk.
Can you hear me?
Yeah.
So yeah, hi Tim. Thank you for the talk. My question is, if parallel access is supported, for example, if you have multiple MPI processes accessing a tile.
And so if you have just a single tile, then your parallel access is the same as it usually would be. You can't have two threads accessing the same array element without possible race conditions. But the idea is that you may, if you require parallel access to full array tiles, you can duplicate versions of these, you know, say in different NUMA domains, using using the configuration API for interface construction. So you might request a space in DRAM and then request an interface that allocates in a specific NUMA domain. And then you might create multiple tiles for different NUMA domains to ensure that you have safe parallel access, and pass these off to different threads. You know, that's one approach that you could use. And I mean, inherently, the structures we use are so our API is thread safe as well, if that was sort of an underlying query in that question as well. So we sort of ensured thread safety where we can.
Okay, thank you.
Okay, so thank you so much, Tim, for your presentation, also for the rest of the attendees for your questions. So let's go for the next presentation from João Pedro Barreto from the Instituto Superior Técnico de Lisboa. Bem-vindo, João.
Okay, hi, thanks. I guess you all see my screen.
Yes, at least I can see it. Yeah.
Perfect. It's always really tough to give this sort of virtual talks without seeing your faces. Okay, so thank you for the introduction. So yes, I'm a professor at Técnico in Lisbon, and also a researcher at INESC-ID. My talk is about part of our effort in the EPIC project, where we also have a relevant part in the same work package where Marc just already told us about their efforts. Okay, so I'm leading the INESC team, and my purpose today is to tell you about our complementary efforts in this work package. So the problem that I will focus on this talk is the same problem that every talk has focused so far. So it's about giving some memory system, where should we place the data of our application, okay, the data placement problem. And let's start by recalling what is the traditional landscape, okay. So traditionally we have our traditional memory hierarchy, and we have learned for decades that we can build nice solutions to the data placement problem by relying on some fundamental assumptions. First of all, is that traditionally the layers in the memory hierarchy, they differ by orders of magnitude. Okay, either we look at them in cost, capacity, or performance. Second assumption is that usually the application thread, so the code that is run, the program that is running on the CPU, this program can only access directly the topmost layer, which we usually call the cache. Okay, so the lower layers, they are used as some backup layers that are not directly accessible by the application. Third assumption is that typically the higher layers in the memory architecture, they have symmetric or very symmetric load store performance, and that helps us simplify our data placement solutions. And finally, all the threads observe the same memory hierarchy. Okay, this is a somehow simplified view, but this is captures quite well the traditional landscape. Of course, we know that things are changing. Okay, and now we have well, heterogeneous memory systems are here to stay, and so if we look at one socket in a modern HPC machine, we have different kinds of memories. I'll not tell you about this because we have been talking about this variety of different memory types in this workshop. And besides this hybrid mix of different memories, we also have, typically we have multiple sockets in the same machine. This is also a very prominent norm today. And this means that we have hybrid nodes, multiple nodes that have this hybrid mix. And many of these memories, they are also directly accessible across different nodes. So we have what we typically call a non-uniform memory access, so a NUMA system, okay? And as I told you, so we are also part of the Heap project. Our team is also working on along with the BSc team with Marc and all his colleagues. And we are focusing on different, in the Heap project, we are focusing on this data placement problem for heterogeneous memory systems from different perspectives. So in one of the axes, we are looking at not just hybrid memory systems, but we are also looking at heterogeneity from the perspective of having multiple NUMA nodes in the system, okay? And we are focusing on tackling the problem from two main perspectives. And of course, we are also trying to find synergies between these two perspectives. Marc has already told us about the ongoing efforts on the object placement allocation level side in the Heap project. My talk will be mostly focused on complementary roadmap that we are also following in the project, and then I'll be looking more at dynamic, transparent, OS level solutions, okay, that focus on placing pages, okay. Of course, there is a nice complement, and also in the Heap project, we are also, it's also part of our future plans to combine these two approaches somewhere in the future, okay. So before I tell you a bit about our results so far, let me just give you my personal view on some fundamental implications that memory heterogeneity introduces in the data placement problem. Okay, I'll just briefly mention three key implications among many others. Okay, but these are the three fundamental ones that I believe constitute a higher disruptive obstacle when we rethink this problem with a new kind of architectures that we have today. Okay, so the first major disruption is that there are two fundamental assumptions that we had traditionally that we no longer have. So first thing, we start having adjacent layers of the memory hierarchy that no longer differ by orders of magnitude. Okay, for instance, if we pick the example of DRAM and Intel Optane, now we know that, for instance, for read latency, we are no longer with the distance of 1 or 2 orders of magnitude. We are much closer in terms of performance. Okay, the same thing is also true in the case of NUMA architectures. Okay, so if now we look at the performance of my local memory of the local memory of the node where my thread is running, and if I compare the local performance to the performance of the remote memory node, they differ, but not by different orders of magnitude. The second main thing that has changed is that these different memory nodes, they are now directly accessible. Okay, for instance, and as we have already learned today, the thread running on the CPU, it can directly issue load and store accesses to DRAM and also to Intel Optane if we are using app direct mode. Okay, the same thing is true in NUMA. Okay, we can have pages mapped to the remote and to the local node, and the application will directly access any of these nodes directly. Okay, so this means that we can rethink our algorithms for data placement, or for caching, if you want to put it in this way, by taking advantage of the fact that now we no longer have a single cache, which is the topmost layer through which every access goes through. Okay, now we may intentionally place some data, okay, on lower layers that are also accessible. Okay, and if we do that, if we do it wisely, we may be taking a really good opportunity of getting a higher bandwidth, because now the application will be able to access different data items from different memories at the same time. Okay, so and also we no longer need to be using inclusive strategies, so we also may save space. Okay, so we no longer have the topmost layer will no longer have to hold every data item that is currently being accessed. Okay. The second major implication is that typically when we think of the data placement problem classically, the silver bullet was also always to maximize heat ratio. Okay, when I say heat ratio, I mean maximize the heat ratio of the topmost memory layer, so of the cache, if you want to call it like that. Okay, so this is no longer the optimal strategy in today's heterogeneous landscape. Okay, and I can illustrate this with two examples. So first example is for some important kinds of memory technologies, for instance, non-volatile RAM, we no longer have symmetric load store performance. Okay, this means that we should not just think of heats. We should think of store heat and also load heat, and it may make sense. It may be an advantage if we do things that traditionally did not make sense. For instance, if we need to decide which pages we want to put in DRAM and which pages we want to keep on the Intel Optane memory, it may make sense to place some pages that are more write heavy, okay, because the DRAM advantage in writing is much better than Intel Optane, okay, and it may make sense to put some pages that are read intensive in Intel Optane, even if those pages are very frequently accessed. Okay, so this is we are perverting the typical way we used to think in terms of data placement in the non-heterogeneous times. A second example where we need to rethink our solutions is a consequence of strategies where we do what is typically called the cache bypass. So if now we intentionally place data on more than one memory node, okay, for instance, if we intentionally place data to be directly accessible on DRAM and also Intel Optane node, or in a NUMA case, if we place data in a local and also in a remote node for improved bandwidth, now we need to take bandwidth into account. And I can give you a very simple example that shows perhaps not intuitive case. If our strategy decides to place data items on the topmost or on the memory node with the highest performance, just based on the heat ratio, or if you want on the access frequency to that data item, we may end up putting the most frequently accessed items on the topmost on the memory node with highest performance, and by doing that we may saturate the bandwidth of that node, while the other nodes that have lower performance but they are also there, they may have a lot of unused bandwidth. So this means that if our applications are bandwidth intensive, we should take bandwidth into account. And sometimes it may be better to place some some frequently accessed items on the other memory nodes, such a way that we avoid the bottleneck of putting all the accesses on the fastest node, because that node may become a bottleneck. Okay, so these two examples illustrate why we really need to rethink our solutions, because the optimal solution is no longer what it used to be before this kind of these new kinds of systems. As a third implication, we no longer have a simple memory hierarchy. Okay, this is especially a consequence of the fact that now we have NUMA systems. Okay, so we have multi-socket systems, and even if in one memory node we have if we can think of a memory hierarchy with different kinds of memory, now we have multiple nodes, and the views that these different nodes have of this complex topology may not be symmetric. Okay, just to give you an example, in this slide you can see the topology of a NUMA system. Okay, this is based on an AMD Opteron architecture with 8 nodes. And if in the right-hand side figure, we can see the bandwidth, the node-to-node bandwidth. So if we think, so what this figure is depicting is what is the bandwidth that a thread running on node 1 can obtain by accessing memory on some other local or remote node. Okay, and if you look carefully at the numbers, we have plenty of heterogeneity. Okay, and we have things are not symmetric. Okay, they are just approximately symmetric. Okay, this means that if we want really to, if we have threads running on all these nodes, and if we have pages or objects that are shared between these threads, and if we need to place those objects in some optimal place, this problem becomes a multi-dimensional problem that is much complex than it was in a single socket case. Okay, so in the EPIC projects, so we are trying to look at this new problem, okay, from different perspectives, and this is ongoing work. So what I will do now in the second part of my talk is I want to tell you about our results that we have already obtained while tackling part of this problem. Okay, so in the second part of this talk, I'll just tell you about our work on tackling data placement in NUMA systems. Okay, and we are doing that at the OS level, so we are placing pages, not objects, and we are trying to do this as transparently as possible and in a dynamic way. Okay. So, and by the way, what I will tell you, so it is about page placement in NUMA in a bandwidth-aware approach. Okay, so this is a part of a collaboration within the EPIC project, but also with other people from out of the project. So to redefine the problem very quickly. So I will only focus NUMA systems, and for the sake of simplicity, so we have multiple nodes, and I will just assume that each of these nodes has just DRAM, okay, for simplicity, okay. And we want to decide where we place pages in this case, okay. So we already have this is not a new problem, okay, and we already have some common rules of thumb for handling this problem. Typically, what we do is for the thread private pages, we map them privately. Okay, so the thread private pages of a thread running on node 0 or node 1, we map them in node 1. Okay, and for the shared pages, okay, for pages that are shared across by every thread that is running on every node, what we typically do is we just distribute those pages in some even way across all the nodes where we have threads running. Okay, this is both options are supported by, for instance, in Linux, okay, by Libmemkind. Okay, and these rules of thumb, they typically work quite well. So they are best effort solutions, but they work quite well, as long as we don't have a huge asymmetry in our topology. okay? And also as long as we have threads running on every node, okay? What we did was we looked at a corner case, and so we questioned, what if the application is not running threads on every node? What if the application, for instance, for scalability reasons, it is only running a number of threads that only runs on a subset of nodes? So let me call these the nodes where we have threads, let me call these the worker nodes, okay? So in this case, we'll have threads running on a subset of nodes, and we'll have some other nodes that are not running threads of our application, okay? They may be totally idle, or they may be running some other application, okay? And the question here is, how should we place the pages of the threads that are running on this subset of nodes, okay? Typically, what the state-of-the-art does in this case is, for the shared pages, it places these shared pages, it distributes them evenly across the nodes where these threads are running, okay? What we have found with our research is that this is far from the optimal, this is far from being optimal, okay? For two reasons. First reason, we are neglecting the bandwidth that is available on the other nodes, where that may be idle or may be running some other application that is not memory intensive, okay? Second reason is that if we distribute these pages evenly, we are not taking into account the asynchronous bandwidth that may exist across these nodes, okay? And we found out in our research that we have plenty of asynchrony, so heterogeneity in the topology of bandwidths, okay? So in a nutshell, what we did to solve this was we produced this tool called BWAP, which is short for bandwidth aware page placement, okay? And in a nutshell, so what we did was, our focus was on maximizing bandwidth, okay? So our goal was to consider placing the pages of the applications on every node, even if the threads of the application are just running on a subset of these nodes, okay? And we will do that by taking bandwidth asymmetry into account, okay? So what we do is we distribute pages across every node, okay, the shared pages, but we don't do it evenly. We assign one weight to different nodes, and that weight essentially tells us what is the share of pages that will be placed on that node, okay? And the challenge here is how to choose these weights in an optimal way, okay? I don't have the time to tell you about this, but this is a very complex problem because it depends on deep modeling of the underlying architecture and also on the application-specific access patterns, okay? And in BWAP, we did this with two components, okay? Just very, very quickly. The first component is we have this model, this tool that does a modeling of the underlying architecture, and it calculates an optimal weight distribution, okay, that assumes an idealistic bandwidth intensive benchmark, okay. And based on this, we devise this weight distribution, and with this weight distribution, what we do is when the application itself is deployed, we start by using the canonical weight distribution, so the one that is application agnostic, and then we have this dynamic online tuner that, based on some hardware performance counters, it adjusts on the fly the weights of the page interleaving such that they optimize for this application specific characteristics, okay. Since I see that I'm running out of time, I just got distracted, sorry. I'll just very quickly tell you that we have published the results of this work. We have, to do this, we have picked different bandwidth intensive applications from Parsec, NAS, Splash application suites. And we have compared BWAP with default options available in Linux, and also with some state-of-the-art proposals that have been proposed before BWAP. And we have found that and we have tried these applications on different configurations. And the idea here is so in this slide, I'll show you an example with a machine with 8 NUMA nodes. And what we do here is we run the application on a subset of these 8 NUMA nodes. On the left-hand side, you see how things go if the application only runs in 1 NUMA node while having the other 7 NUMA nodes idle, okay? And then with 2 work nodes and then with 4 work nodes. And what we observed was that especially when the application runs on a subset, on a smaller subset of NUMA nodes, BWAP can get very considerable performance gains compared to the other state-of-the-art alternatives. And the main reason is that we take the bandwidth heterogeneity into account and we optimize for it. Okay, so just to conclude, data placements classically, the solution for data placement, they rely on obsolete assumptions, and we need to rethink these systems. As an example of what we are doing in the Heap project, I have told you about BWAP, which focuses on the problem of data placement, of page placement on NUMA architectures. And if you want more details, you can check our publication on IPDPS, and you can also find the open source code of the tool on the Heap website. And just to conclude, this is just a part of what we are doing in Heap. So if you are interested on this kind of ideas, so just follow the project. Okay, thank you.
Thank you very much, João. That's been a very good talk. Let's see if there are any questions. Please, attendees, raise your hand and we will give you voice, or feel free to use the Q&A alternately. In the meantime, I would like to ask a question. Would you please expand on how you do the mechanism that you do for the online monitoring of the hot pages on that?
Sure. We start by placing the pages of the application, assuming our canonical application. So we start by assuming that we are optimizing for our benchmark that we use to profile the machine. So this is a really symmetrical, very predictable, bandwidth intensive application that is not the same application as the one that is running. And when we do this in the first seconds of the execution time, of course, we get some suboptimal performance. And what we do there is then we need to adapt. And we use online hill climbing, and our metric to guide our hill climbing is essentially stall rate. So stall rate on the memory system. So we gradually try different. We do incremental page migrations from some nodes to the others, and we try to migrate some pages. And if we see that, and after migrating, we measure stall rate again. And if we see that we got better stall rate, so if we see that threads spent less time waiting for the memory system to reply, we know that we got better. So we keep doing it. Okay, and until we get to some point where we see that we have reached some optimal point or some local optimum. Okay. Currently in BWAP, we only do this at the first seconds of the application because this has some overhead, and we have observed that it's not for the applications we have tried. There's not a big advantage in doing this throughout the whole execution time, and this has a strong overhead. So we just do it at the first time, at the first seconds of the application, and we assume that our placement is a good approximation for the whole execution.
Okay.
I don't know if I answered your.
Yes, yes. Thank you very much. Very interesting details. Okay, so I don't see any more questions, and we're a little behind the schedule.
I have a question, if I may, Tony.
go ahead.
So João, question for you is, so have you tried this VWAP on subNUMA cluster on Intel processor? Just for curiosity.
So yes, so the results that I showed, the examples I showed here today, they were, I picked this AMD Opteron machine, which is already a bit old, just to show a strong example with a lot of nodes. In our paper, we also have results with a more recent Intel. I believe it's a Cascade Lake Intel with two sockets in subNUMA mode. In subNUMA mode, we don't observe such evident difference in the performance of local versus remote nodes. That means that the advantages of VWAP are not as evident, okay? But we still find some cases where we gain by using our more sophisticated technique.
Okay, I'll take a look at the paper.
Okay.
So, good. Thank you.
Thank you very much, João. So we're gonna do a break now. There is still a very interesting talk after the break from Adrian Jackson from the University of Edinburgh, and after that, a panel with all speakers involved and open mic. We will keep the original schedule, so we will pause now and we'll come back at 5:30 p.m. Central European time. Thank you very much, and we'll resume 5:30 p.m. Thank you.